Hey, it's Wednesday, Red Ribbon Week, so we were supposed to wear orange today, possibly. So here I am, little burnt orange, hook 'em horns, working a problem with you on forces and angles. This can be found inside of Google Classroom. It was posted as material, and I think material, double check that, could be assignment. But it's called Force Notes 3, Samples to Consider Friction, Angles, and Normal Force. You are welcome to do this as always on a piece of your own paper, but it can be helpful to have the photo, or sorry, have the drawing in case you want to go there. All right, so what we have here is a box being dragged across the floor. It's being dragged by a rope, presumably. It doesn't really say exactly what it is, but there's some roughness to the floor because we're given a coefficient of friction. We're going to have to deal with that, and it's asking for a whole bunch of stuff. It wants to know the net force in the x direction, the net force in the y direction, the weight of the box, the normal force on the box, the frictional force, and the acceleration. So we're told first to do this problem algebraically. All right, so I see this, and I'm going to start in the x direction because that's what looks interesting. That's where the friction apparently is going to be at work. So if I sum all the forces in the x direction, I need to draw them, don't I? Okay, that drawing that you've been provided with is not good enough for a free body diagram. You can definitely do work on it, but remember that you need a free body diagram that's just a little box or a fat dot. Maybe to emphasize that I'm not drawing the box, I'm just drawing a point of mass. I'll make a fat dot this time. So there's a pull in that direction, right? So I can say P for pull, and it would be fine if you wanted to do something else like T for tension, but I'm going to have P for pull. There's weight straight down to the center of the earth. So I've got W or mg if you prefer. And then I'm told there's friction, so there's going to be friction going backwards, right, in that direction. And, oh yeah, I have the normal force. So there's my normal force. Okay, so that's my picture of all the forces. Those are all the forces I can think that are going to be on it. So you can do useful things over here, like make components appear. But remember, if the AP College Board wants you to draw just a free body diagram, they don't want to see the box and the floor and your components. They want to see just a single object with all the force vectors acting on it. So when I start summing the forces in the x direction, I realize I don't have this here, add that one. So there I'm making this a useful force diagram, I'll call it. There's weight down, there's normal up. I'm regretting I hadn't left a little more room here, but that'll be fine. So when I start summing all the forces in the x direction, I space things out so it's easy to see negative signs. And I have friction in there, and now I go, this rope, or whatever it is, represents a pulling vector. That's a force, but it's not parallel to friction. So what I'm going to have to do is break this force apart into components. So pull in the y direction and pull in the x direction. Hopefully that looks familiar to you. Just picture, a soccer ball being kicked, right? When we were first learning components, we were using velocity vectors, but the x component is just going to be the original vector times the cosine of the angle. So I'll call that one p cosine theta. And the vertical component will be p sine theta, like that. So in order to have all my vectors parallel, acceleration in the x direction right here is embedded in that summation of all forces, right? So if I want acceleration in the x direction, I need to have friction in the x direction, and I need to have the pull in the x direction. So that's going to be px. Okay, so I'm going to make one thing negative because I have something negative and something positive, and work this way. So substituting in for friction, can you tell me what I'm going to put in there? Bet you can. I'm going to go mu times the normal force. And then px is going to be p times, go ahead and put your component in, the cosine of that angle. Remember, we're told to solve algebraically first, so I'm not going to rush to put numbers in. Ordinarily, what do we do next? Well, ordinarily, the next thing we do once we continue our algebraic substitutions is we put in an mg right here. So that would become mu mg. But we cannot do that today. This is huge, really important point to recognize. Let me show you why not. Let's try summing all the forces in the y direction. I'm just going to come over here for a minute. The sum of all the forces in the y direction equals, or if you prefer, mass times acceleration in the y direction. Well, let's see, I have the normal up, and oh yeah, there's this component of the pull that is upward. So I have the normal up and I have py up. What else do I have? I have weight down. Do you realize that this means the normal force is not equal and opposite to the weight? If these things all have a mass times acceleration of 0, because the box is not flying up in the air or breaking through the floor, then that means the weight force down is balancing two forces that are up, okay? So I've reversed things a little bit. I added W to both sides, and I'm looking at it this way. In other words, the normal force is going to be equal to the weight minus the amount of lift that's coming from the vertical aspect of that pull. Whoa, okay, so when I have more than one vertical force, the normal force is not going to be equal and opposite to the weight. So I'm going to have to take this expression that I've got and use a systems of equation approach and bring it over right there to be used in my friction equation, because that's my normal force, okay? All right, I think I broke that pencil point. Let me try another one. So here we go. Algebraically now, mass times acceleration equals the negative of mu times, this might be a good time for a bracket. I'm going to put a bracket around this. And I'm going to substitute in for the normal force. W minus Py, close bracket, plus P cosine of theta. Okay, kind of a mouthful, isn't it? So now how would I go about substituting in? Well, let's see. One of the things I would like to do is get acceleration, right? So I'm going to divide both sides by m, so I can do that now if I want to, and come up with an equation for acceleration. And I think I'll also put mg in right there. So let's see how this would look. A equals negative mu times my bracket, here's mg, minus py, close bracket, plus p cosine theta. Okay, how much have I done? Well, let's see. I've got an expression for acceleration. I've got an expression for the normal force. I've stated, kind of weirdly, but I've stated that the net force in the y direction is equal to 0. And apparently there is an acceleration here. So let's see if we can find that numerically now. I think we've done a pretty good job about working out these things algebraically. We're going to have to come back at some point to actually calculate what friction is, right? Friction is going to be mu times the normal force. So I'll go ahead and put that down. Friction is mu times the normal force. So therefore, friction will be mu times, another bracket if you want to, W minus Py. Can you see that all the way down there? I'm just sort of setting up a place where I will remember to come back and calculate a numerical value for friction also. Because one of the things you might want to do is sort of check these things off when you have a long list like this. Okay, so looking right here, I have to take all that and divide by the mass. Sorry, I left that off at first. There's my acceleration equation. Okay, so let's see if we can substitute in for that. Acceleration equals, well, we're told FloJo is pulling this box. I don't know if you know who FloJo was, but FloJo was the fastest woman in the world in like 1988, I think it was. And she set 2 records that still stand today. There aren't very many records in track that last, what, more than 30 years? So she's pretty amazing, principally a sprinter. So anyway, this might be fast, we'll see. So I have a coefficient of kinetic friction of 0.3, so negative 0.3. Here comes a bracket. Now I have to put in a mass of a 5 kilogram box. So I'm going to go 5 times G of 9.8, so maybe some parentheses there will help me sort things out with my bracket. And then I go minus Py. Oh yeah, I'm going to have to reach up there to get that. That's P times the sine of theta. So that's going to be a pulling force of 65 newtons. So 65 times the sine of 30 degrees. So I'm reading this last line up here at an angle of 30 degrees. Okay, so I've got the bracket now, so I'm going to close the bracket. Okay, plus P cosine theta. So this is going to be plus 65 cosine, I'm running out of room here, aren't I? 30 degrees. Here, we'll make a little sidebar over there for our friction. Okay, try to organize your work. Maybe you can organize it better than I did, but at least delineate it so that the reader can tell where to go. And then I have to remember that acceleration is net force divided by mass, so I'm going to divide the whole thing times 5. Okay, it's calculator time. I'm going to put it in slowly, so that means I expect you to be putting it in on your calculator and see what you get. We'll see if we get the same thing. Personally, I like to start inside the bracket when I have something complex like this and then go outside of it. So I'm going to start off with 5 times 9.8. And of course, you want your calculator in degrees. You know, one of the things they asked me for is the net force. So I think I should probably put that in. So I'm going to go A equals sigma F over M So right here, I can record one of the numbers I have in my calculator, which was the net force of 51.34165. So I'm going to do that because there's my net force in the x direction. And then when I divide by 5 kilograms of mass, that's a rounded number, by the way, but I'm dividing by my unrounded number. I got 10.268. So I'm going to call it 10.3 meters per second squared of acceleration. If you didn't get that, go back and try it again. Okay, so what do we have? Let's see. We have the value for the net force in the x direction, that's in newtons. We have the acceleration in the x direction, that's in meters per second squared. We haven't yet calculated what the normal force was. So let's go back up here and do the normal force now that we're going numerical. I guess I can switch back to ink again. So here the normal force is equal to, this is going to be mg. So 5 times 9.8 minus 65 times the sine of 30 degrees. So please calculate that normal force now. I'll do the same so you have a little time. And I got 16.5 newtons for the normal force. So I might box that also to make that number easier to find. I'm going to need that number down here, aren't I? I guess I could just put it right in and sort of use my numbers bank. So when I find friction down here to put in mu times the normal force, I'll just use my 16.5 newtons that we just calculated. So mu, friction, is going to be equal to 0.3. I don't have to make it negative when I'm looking for the frictional force. It's fine. My picture indicates that it's backwards, so you could make it positive or negative. Either one would be absolutely fine. Don't sweat the small stuff. Let's go times 0.3. Frictional force was 4.95 newtons. No wonder it was accelerating so quickly. That is a really big acceleration, right? Think about how fast free fall is. That's faster than free fall. FloJo was pretty fast. Okay, so numerically, you should go back if you were doing this and check that you've solved for everything. I found the weight right here is 49, so I might need to write that down someplace if I were really being very careful to present this, like in homework where I'm looking for all my answers. But the idea here is that you have to use a systems of equation approach because you have to work the normal force. You have to work the vertical forces in order to find the normal force. And then that's what's going to get substituted in your x direction when you're working with friction. So that's the big picture. It's a lot going on when we're at angles. You've been hearing me say this is true as long as you have a horizontal surface. This is true as long as normal and weight are your only two verticals. That was when we were saying that the normal force was equal and opposite to the weight in magnitude and direction. But we've got some fill in the blanks at the bottom, so let's take a look at those. Ooh, take a deep breath. Look at how much you did first. Do you realize how many multiple choice questions could come out of that? A lot. I hope you do realize that. Okay, so when I come down here, I've got a little paragraph with lots of blanks in it, so let's try this. Fill in the blanks. Whenever a push or a pull with a vertical component, because FloJo was pulling up as she pulled forward in this example, is applied to an object on a surface, the normal force will not be equal and opposite, meaning, of course, equal in magnitude and opposite in direction. It still will be opposite in direction. Will not be equal and opposite to the weight. And if you want to do the Department of Redundancy department, you can say the weight force, okay? So the normal will not be equal and opposite to the weight when you have a vertical component that's in there in addition. So the rest of this little paragraph is an opportunity to study. So we're kind of hammering it in, saying the same thing again. Whenever there's an angle involved, either because force is applied at an angle, okay, that's what we just did, or check this out, this is new. The surface is not horizontal. It could be an angled surface. I don't immediately know what the normal force is. I don't know what the normal force is when there's an angle involved, okay? Or for that matter, when there's a vertical lift or a vertical push, okay? The normal force will not be equal and opposite to the weight. Hammer this point home in your brain. The normal force will not be equal and opposite to the weight, okay? Here's an opportunity for a math symbol. The normal will not equal mg. Okay, all right. So you did this asynchronously, which is good. And what you can do now is do a little practice without me asynchronously. These are sample problems. These are practice problems for class practice. I don't mind putting you in groups for this. We'll probably do that soon. And I don't mind going over these with you. We'll probably do that soon. okay? But here's another problem, no pictures this time, but you have something pulled at an angle and you're challenged to find the normal force and then the coefficient of friction. And here's something else where you're pushing. Now, if you push a piece of furniture across the room, you may find that you're pushing down at an angle because you're taller than the piece of furniture. So in that situation, you also mess with the normal force. So I hope that works for you. I'll see you back in class quite soon.